Okay, so for this question, we have an oil drop that floats on the surface of water and is viewed overhead when illuminated by sunlight shining vertically downward and reflected vertically upward. Okay, so if we draw this, we're going to end up with something like this. This is going to be our oil, this is going to be water, this is going to be air. Now, sunlight is going to come down and be reflected off the air-oil interface, and then it is going to be transmitted through the oil and also reflected off the oil-water interface. Okay, the refractive index of oil is 1.20, the refractive index of water is 1.33, the refractive index of air is 1.00. Okay, are the outer, thinnest regions of the oil drop bright or dark? So our oil drop looks something like this. So it's not quite, it's more spherical. I've drawn it here just as like a straight surface, but what it's probably going to look like is something like this. So what we're asking about is these regions here, are they going to be bright or dark? For each ray of light coming in here, what are our phase changes going to be as the ray hits each interface? So when the rays hit the air-oil interface, there's going to be a pi phase change. And similarly, when they hit the oil-water interface, there's going to be a pi phase change. And that's because the refractive index of oil is greater than air and the refractive index of water is greater than oil. Okay. Remember also that the width of the oil drop is going to be L, and it's going to be smaller. The width is going to be smaller at the point where it is thinnest, and L is going to be larger at the point where it is greater. Let's have a look at our conditions for constructive and destructive interference in these instances. Okay, so for constructive interference, remember we've got two phase changes. Therefore, the path difference, which is going to be 2L, is going to we're going to have constructive interference when the path length difference is going to be some integer of the wavelength of light in the oil. And so therefore 2L is going to be m lambda divided by NO, where lambda is the wavelength of light in a vacuum or in air. Okay. So that's fine. We've got two phase changes. That makes sense. Therefore, for destructive, we're going to have the opposite case. So we're going to have 2L equals m plus a half. Lambda O, or 2L, is going to be m plus a half lambda divided by NO. Okay, so in both cases, remember, we're going to have m equals 0, 1, 2, etc. Let's work out what our conditions for L, for the width of the oil droplet, are going to be to meet both of these instances. So we're going to have m divided by 2, lambda divided by refractive index of oil, and then here we're going to have m plus a half lambda divided by 2 refractive index of oil. Okay, so essentially, what is going to happen? We're asking what's going to happen as L approaches 0. Remember, so in these outer parts, this L is quite thick here, it's quite large here, but as we get to the outer parts, what's going to happen to L? As L approaches 0, that must mean that M is going to approach 0. So as M approaches 0, what's going to happen is our path length difference is going to get smaller and smaller and smaller. So right at the absolute edges, as m approaches 0, that suggests that there's going to be no path length difference. And if there's no path length difference, given our conditions, that must suggest that we've got path length differences that are integers of the wavelength. This suggests that at the absolute edges, we have to have constructive interference. Because, remember, for destructive interference, this has got to be our condition. So as m approaches 0, the width of the oil drop, or the path length difference, is going to approach a quarter of the wavelength of light in air. But this is actually going to be smaller than that because we're approaching 0. So part A is the outermost edges are going to be bright. Okay, part B. Moving from the rim inwards, this way, to the third blue band and use a wavelength of 475 nanometers for blue light. Determine the film thickness at this location. So we want the third blue band. So remember, right at the edge, this is going to be our order number of m equals 0. Then we're going to have the next blue band is going to be n equals 1. We want the third blue band to 3. So this is going to be m equals 3. Okay, so therefore we're going to use our equation here for constructive interference. 2L equals m lambda divided by n O. Therefore, L is going to be m lambda divided by 2NO. Okay, so now we just sub all of our stuff in. And when we do that, we get 594 by 10 to the minus 9 meters, or 594 nanometers. This is a very, very thin droplet. Part C, if the oil thickness increases, why do the colours gradually fade and then disappear? Okay, so as the oil thickness increases, what we're essentially doing here is we're not going to have a thin film anymore. So if we don't have a thin film anymore, what's going to happen is these two reflecting surfaces, so off the surface of the oil drop and off the back surface connecting the oil to the water, they're going to be too far apart. They're going to be so far apart, in fact, that the light rays of both surfaces are not going to be coherent anymore. So that's what's going to happen if as we increase the thickness of the oil droplet.